Hello everyone, this is group number 17. My name is Aaron Shi. The topic of our group is flying pendulum clocks. Then this report is our final project report. This part is the outline. There are 4 main points. The first is that we will introduce what a flying pendulum is and why we choose this topic. The second is the theoretical part, which contains all the mathematics of our topic. The third is simulation. We will use the Python taught in class to solve this problem. Finally, the actual results. We will analyze with some experimental results. Okay, let's start the first part of the introduction. The first thing we want to introduce is, what is a flying pendulum? Flying pendulum is a clock that uses a flying pendulum escapement mechanism. Maybe it's not so clear just in words. So, we found a manuscript map of flying pendulum clocks. It looks like the picture in the upper right corner. That's run in. Different from the structure of ordinary simple pendulum. It is mainly composed of a pillar in the center and 2 structures on the left and right. Then it will do periodic motion on each column separately. So, with such a mechanism, we want to take advantage of its periodic motion properties to calculate the time. And it has 3 main phases. The first phase is the small post on which the rope has just been hooked. The second phase is when the rope goes around the small column above, wraps around the column below, and bounces back due to inertia. At this time, it will enter the third phase, and the rebound process will release the small column hooked by the first phase, and then do the same winding movements on the lower column. Due to its design have 2 sides, the same movements will occur on both sides, and the cycle will be completed. Okay, after introducing what a pendulum clock is, what we want to talk about is the motivation for our group choice. The first point is, the flying pendulum clock is actually designed by Leonardo da Vinci. Da Vinci is a genius of the century in history. Our group is very eager to reproduce his experiments. Maybe we can use what we have learned to discuss and analyze or even improve it. The second point, we found that when mention of measuring time, many people use ordinary pendulums and then adjust some variables. But what we want to do is not a boring experiment. We're enjoying a special design. At present, there is no open source analyzing flying pendulum clocks, so we want to take this opportunity to do it. The third point, indeed, is that this design is complete enough for the topic to allow us to analyze some of its motion and mathematics. Okay, we are going to introduce the math.
Now, I'm gonna introduce the math behind the system. First, we separate the time to 3 parts. The first part is the time that flying pendulum open from the pillar, and the second part is that flying pendulum tied to the pillar, and the third part is flying pendulum swing around. Since the third part is constant and we will not having much time dealing with it, and first, I'm gonna figure out the opening time of the flying pendulum, and we'll figure out in physical way. Let's take a look to the graph, and we assume T equals to the pulling strength of the wind, and mg equals to the pulling strength of the gravity, and we have the first formula, T sine theta equals to mv power 2 divided r, and the second formula, T cosine theta equals to mg. And we combine these two formulas together, we get the third formula. G divided cosine theta equals to V power 2 divided R sine theta. And we also know that V equals to 2 pi times R divided T. And this little t means the period of the flying pendulum. And we take V back to the formula 3 and we get G equals to 4 pi power 2 times R times cosine theta divided T power 2 times sine theta. And then we get the period T equals to 2 pi times square L times cosine theta divided G. Let's write down the differential equation. We know that dl equals to 2 pi r as the circumference of the pillar divided sine theta times dt divided big T. And big T now means the period of the flying pendulum. And T equals to 2 pi times square L times cosine theta divided G. And we get the differential equation dl dt equals to R divided cosine theta times square G divided L cosine theta. And in this pendulum, we assume that no collision of the mass with the pillar. So speed of the mass should be close to 0 from the beginning, but this would make the time more than 10 seconds, and it is not really possible. Then we have to have a second way to figure out the opening time. We will solving the equation in energy way, and we get the h of t, and h of t means the height of the mass, and divided t dt equals to v tangent t divided tangent, and we get the v of t and divided the h equals to 2 times g. And in this formula, we get v of t equals to 0. And this is impossible. And we also consider no collision in this. Finally, we would like to find out the tying time of the flying pendulum to the pillar. And we solve this problem in physics way. We know that r prime of t equals to minus r times omega divided cosine theta, and omega power 2 r of t equals to ac, and this is because it's circular motion, and we can get the final formula dr of t divided dt equals to minus r times ac divided r of t squared divided cosine theta. And this is possible because we solve this equation and the time is less than 1 second, but it may crash the pillar in the beginning, so this system is not really stable.
The first part of our code is importing library. And I basically copy it from the previous quiz. So actually most of it are useless. and are useless. And the method we use is actually simple SymPy. So maybe the most important part is the SymPy part. For example, from SymPy import symbols and so on. The second part of our code is the uh, our first attempt to get the time. And first, we define some symbol like t means time, and the time means that the time that the ball spent to tangle onto the chopstick, and h means the length that the ball drop or the ball race while it's is tangling onto or leaving the chopstick, and v means the velocity. Tangent means tangent. So basically, our first attempt work on two equation. First equation is that dh over dt equals to the velocity over tangent theta, and this equation is came from the triangle that the ball create while it's move forward. Actually, it's a circle, but in a very small in a very small time. It looks like it moved forward and also it dropped for a little distance. So we'll get a triangle. Yeah, and the second equation is that dv over dh equals to 2 times of the g. G means 9.8. Yeah, and this relation came from the relation of the gravity potential energy and the kinetic energy. So if we combine these two equations, we'll get the function we need, which is dv over dt equals to 2 times of g and multiply v and over tangent theta. However, when we solve this equation, what we get is that v equals to 0, and it's basically obviously wrong. So we give up of this relation and we move on to another path. So the third part of our code is the second attempt to solve the time. And this time we also define some symbols, and most of it are the same, but this time we'll need AC. And AC means the centripetal acceleration, and it's 上升加速度 in Chinese. Yeah, and it's important in physics because in our relation, actually, we work on the first relation. So dr over dt equals to minus big R times omega divide cosine theta. So this relation is actually it's also about the little triangle that uh, the the ball create when it's tangling on or off the chopstick. So it's actually quite simple because anyways, the length of the cord is basically R. So if it move forward for a little bit, the length that it tangle onto the chopstick can be implemented as this equation. And we also need another equation to get omega, and the omega came from the equation of the centripetal acceleration, which is AC equals to omega times r. Anyways, if we combine these two equations, we'll get the equation we need, and it's quite complicated. Anyways, but we solve it with SymPy and with some parameters, we'll finally get the time equals to 0.78728 and so on. It's actually really close to the practical experiment we did. So I guess this maybe is the true relation of the time and the chord and so on.
So I'm going to talk about the flying pendulum we actually made. Here are a few short clips of it.
Yeah. Oh. Oh.
As you can see in the video, we use bamboo chopsticks as the stand and a cardboard box as the base. The force to give the rotation is rely on a toy pullback car. The single pendulum is tied to the bamboo chopsticks with marbles and threads. During the actual operation, we found that the force given by the pullback car was not enough to make the marble wrap around the chopsticks, so we applied force by hand to make the rotation speed a little faster so that it could wrap on the chopstick, and then we can get the data. And it can be seen that the time for the marble to wrap around the chopstick is about 0.7 to 1 second, and the time to unwind it is about 1 to 1.4 seconds. So the time is able to be tested. And when the given rotation force is fixed, its elapsed time is fixed, so it can be used as a tool for measuring time. This is probably our experiment, and there's some other videos about it. And you can see in this video we upside down the base to make the pullback car to spin better, because if we put it in the right way, in the up way, sometimes sometimes it will stuck when it's spinning, so we put it upside down to make it to spin better. And that's all. Thank you.